Let's go ahead and get started. Vasil or Oksana, do you want to introduce Jack for 1 second?
Yeah, I can do that. So Jack has been working on the automatic differentiation, and he will be talking about his recent progress on implementing Hessians. And Jack, the stage is yours.
All right. So I'm the responsible for CLAD, the client plugin for automatic differentiation. During this presentation, I might refer to automatic differentiation as AD. This is just for simplification. And before I begin, I'd like to thank my mentors, Alexander, Vasil, and Oksana, for their ongoing support of me during the summer. So without further ado, let's begin. So automatic differentiation. So in an introductory sense, AD is essentially when you break down a function into a series of sub-expressions or a sequence of elementary operations, and then you try to apply the chain rule onto this series. And generally, AD can be split into 2 modes. The first mode is the forward mode, and the second is the reverse mode. And in the forward mode, when you apply the chain rule, you try to fix the differential with respect to an independent variable. So you try to traverse the chain rule from the inside to the outside. And in the example, in the graphics below, say that you have a function z equals x1 times x2 plus sine x1, and you want to find the differential of it. You basically try to expand the differential on the right-hand side until you reach a sub-expression that represents an independent variable. And on the computational graph on the right, you can see the breakdown of the function onto sub-expressions. And the forward mode is implemented in CLAD through CLAD differentiate. And the reverse mode is very similar to the forward mode, except when you apply the chain rule, you basically try to fix the differentiation with respect to the dependent variable. So you try to traverse the chain rule from the outside to the inside. And as a consequence, the reverse mode is very effective for when you have a function that has a large number of inputs or a large number of independent variables, but it also requires a significant amount of computational memory. And it's implemented in CLAD through CLAD gradient. So just a brief rundown of what CLAD is and how it's implemented. So CLAD basically uses the Clang compiler to perform source code transformation. As far as I know, CLAD is the only C++ AD tool that uses source code transformation. Other tools use something called operator overloading, and in those cases, you have to use custom types to perform AD. But the drawback to that is that there's a lot less portability to the code, and there's a higher learning curve. But with source code transformation, you can use built-in types, and it's a lot more easier to learn. So CLAD, how it works is that basically when you give it a function, it tries to generate a AST of it, or an abstract syntax tree of it, and you can see an example of it on the right. It traverses through this AST through something called Clang statement visitor, and through traversing something like this translation unit decal, it tries to build a derivative function based off it. And CLAD can perform both forward and reverse mode AD. Currently, the range of what CLAD can differentiate is quite broad. It can differentiate built-in C++ scalar types, so like your doubles, your floats, your ints, and it can also differentiate built-in C input arrays. And it can also differentiate functions that have an arbitrary number of inputs, but it can only differentiate functions that return a single value. So something it can't differentiate would be something that would be a function that, for example, returns void, but it changes values in a certain output array. It currently can't do that, but we're currently working on it. CLAD can also differentiate loops, conditionals, and it can also differentiate class methods. But right now, it can't differentiate class methods with respect to member fields. So this is just an example of what CLAD differentiate is. So say that you have a function f cubed add 1, which is basically a cubic addition of 2 cubics, and you want to find the derivative of it. So when you call CLAD differentiate, it automatically generates a function that's a derivative of it, and in this case, it's the derivative of the original function with respect to the variable a. CLAD gradient is very similar, except when you call CLAD gradient, it differentiates f cubed add 1 with respect to all input variables, so a and b, and it stores the differentials in a C array. So summer I worked on creating a way for CLAD to generate Hessians of a matrix. So this is just a brief rundown of what Hessians are. Hessians are a square n by n matrix containing all the second order partial derivatives with respect to all inputs. You can see a mathematical representation on the right. It's very useful for optimization problems and as a second derivative test. It's implemented in CLAD by first. So say that you have a function and you want to find the Hessian of it. You call CLAD Hessian, and CLAD Hessian basically calls the forward mode onto the function. So you would find df dx1, for example, and then it applies the reverse mode onto df dx1. And then what that does is that you essentially get the one column of a Hessian, and one column of a Hessian is represented by a generated second order derivative from CLAD. And so CLAD Hessian, using this method, it iteratively calculates each column of the Hessian at a time, and then it gets a series of second order partial derivative functions, and then it combines it calls all these second order second derivative functions into one single function, and then this single function basically creates an array. So it might be very hard to understand right now, but in this example, I'll give you an example. So here you have f cubed add 1, and then you call CLAD Hessian on it, and then CLAD Hessian, it basically generates a function called f cubed add 1 Hessian, which contains the second order partial derivative functions generated. So you have which are represented by f cubed add 1 drg0 grad and f cubed add 1 drg1 grad, and find the Hessian. You basically call execute, which is call execute. You basically create an input array. You initialize an array for the Hessian to be stored on, and then you call execute on the function, importing values for your independent variables, and you essentially get a 1D array. We initially tried to make CLAD Hessian work with a 2D array, but we got a lot of trouble with resolving how pointers worked with 2D arrays in C++. And in the end, we couldn't resolve it neatly, so we decided to just leave it as a 1D array for now. And so essentially right now, this 1D array on the bottom left-hand corner is representative of a matrix, which is representative of the matrix on the right-hand side. And regarding future work for Hessian, so it'd be good later on if we could find a way to calculate the determinant of a Hessian matrix. Given how a matrix can be of an arbitrary size, right now it's very hard to find a efficient, neat way to calculate the determinant of a arbitrary n by n matrix. There's also the issue of resolving the 1D array issue that I talked about earlier. And we would also like to see CLAD Hessian implemented through a row by row approach. So this is basically just reversing the order in which forward mode and reverse mode is called. So in the row by row approach, you would call CLAD gradient first, and then call CLAD differentiate later on. And we'd like to benchmark that approach and see how it compares to the approach right now. And also, I did talk about Jacobians right now, but since that's a work in progress, I won't get into too much detail in Jacobians because the details of it may change during implementation. But to put it simply, right now we're trying to build upon the reverse mode visitor of CLAD gradient. And finally, we'd like to find a way to mix and match the forward and reverse mode of the CLAD API. So finding a way so that CLAD differentiate and CLAD gradient can be used together. I tried fixing it during the summer, but we realized that the Clang version that CLAD uses right now, Clang 5.0, it needs to be upgraded so that it can use Clang functions which were implemented in later versions. So yeah, this is the GitHub repository of where CLAD is stored. So if you want any more information, you can just visit the site. Yeah, that's basically it.
Cool, thanks, Jack. Are there questions?
This is really amazing. I'm a little bit scared by if anybody will be capable to evolve this, except for you, Jack, and maybe Vasil. How difficult is it to understand how this is implemented? I think because it's algorithmically very complex, even documentation isn't probably going to help, right?
Yeah. So yeah, initially I had trouble. Like I was reading a lot of papers on automatic differentiation, and it was very interesting to see theoretically how it's laid out, and the difference, and how it's so different to how, it's somewhat different to how it's done practically. Yeah. So in CLAD, I thought it was quite weird seeing how it was implemented compared to how papers laid it out.
Yeah, but it's even more impressive that you managed to get this done. It's really, really nice. So we don't have numbers yet on the performance, or do we?
I plan to do that before the evaluation.
Awesome.
But right now I don't have it.
Thanks.
So a simple question, just because I think I didn't understand. Back on, I think it's slide 5. You're talking about what can be differentiated, and I think what you mean by the first bullet is functions is really that you can differentiate functions that return built-in C or C++ scalar types. Is that what you mean?
Yep.
Okay. Okay, cool. Now I understand what you mean. I was lost. So the return type can be an array or a scalar essentially, and can take as many input variables as you want. Okay. Oh, that's cool.
Yep.
Yeah. Okay. Yeah, definitely the performance numbers are definitely interesting. Okay. Any other questions?
Maybe a little bit on the Jacobians. So, Jack, could you estimate how much of work is necessary to get the Jacobians done? And is it something that you would be interested in continuing outside of the HGCal program?
Regarding the work, I think the bulk of it is already encapsulated within reverse mode visitor in CLAD gradient. I think I just need to make a fair number of adjustments here and there to make it work. But regarding working on Jacobians outside of GSOC, yeah, I'll be interested in it.
So my assumption is that I'm not, well, I'm interested in having this implemented, but also I don't want to lose your work, because it seems like you have done some of the work already, and maybe it's not in a state where I can commit. I'll be interested to have it in some form which is, which is ready to be committed, so that it does some basic functionality, although it doesn't really work 100%, that should be fine. So do you see that we can make it in such a shape so that we can set it without jeopardizing or without risking to lose that work that you've been doing?
Yeah, definitely.
Okay, sounds good. If there are no other questions, I just wanted to say that I'm really impressed with what was done over the coding period. So we started off with a proposal. Well, Jack wanted to do something else initially, so he wanted to go for the global module index, but then he joined late, and then I asked him whether he wants to do the automatic differentiation stuff, and the amount of learning and progress he did in understanding those concepts was impressive to me. We put up a plan which was quite ambitious. We didn't achieve the overall plan 100%, but what we achieved, I think, makes me happy. And I would like to thank Jack on the work that he has been doing for the automatic differentiation, and definitely we were going to use his code more and more often.
Cool. Thanks, Vasil, and thanks again, Jack. We go on. Let's see. Actually, I guess Vasil or Oksana, it's you again to introduce Arpitha.
Okay. We have Arpitha. She has been working with us on the global module index. She has very good understanding of how the C++ modules and the global module index work. So Arpitha, it's your turn.
Hi everyone, I'm trying to share my slides.
need some help, or you want somebody to share the slides for you?
Yeah.
Okay.
I need to get the extension right to be able to share.
Okay. David, Roxana, could you share for Arpitha?
I think I can share. Give me a second. Probably sharing. Yeah, so just tell me when you'd like to go to the next slide, and then I'll keep.
Yeah, thank you. Okay, so over the summer, I've been working on the implementation of global module index in root and Cling. My mentors are Luca, Vasil, and Oksana, and I'd like to thank them for all the help over the summer. Could you go to the next slide, please? Hello. Can you hear me?
Yeah.
Yeah, we can hear you.
Next slide, David.
Next slide.
On my screen, I went to the next slide. You don't see it?
Not yet on my side.
No.
Now it changed. It changed.
Oh gosh, it took 20 seconds then. Okay.
Okay. So coming to the motivation of using C++ modules, root requires a lot of libraries to be included. So like textual includes become expensive and fragile. If precompiled headers or PCH is used, the entire header information is in a single file, which is monolithic. And using precompiled modules or PCM solves the problems with the About-to techniques, and it helps provide better performance. Could you go to the next slide, please? Global module index implementation is an improvement to this use of modules in root. As can be seen in the given figure, global module index is basically a table of symbols mapped to the PCMs or modules which contain them, which is created at root startup when no modules or IDX file is found. And whenever whenever an identifier is encountered, if root or Cling or Clang do not know about the identifier, the global module index is looked up. And since the global module index is an on-disk hash table of these identifiers to the modules which contain them, if the global module index knows about these identifiers, the corresponding set of modules is returned and they get loaded. If not, an error is issued. So this global module index implementation is basically a performance enhancer because a list of the modules is already for every identifier is already known, and hence only the required modules can be loaded at startup time. Could you please go to the next slide?
I did go to the next slide. Maybe it's
Okay.
slow again.
So this slide explains my problem statement where the definition of global module index is present. Could you go to the next slide again? And the slide after that too. Coming to my first coding phase, I first worked on okay.
We lost David, so we lost sharing.
Okay, I'll try sharing my screen with you guys. Can you see my screen?
Yes, cool.
Okay. So yeah, this is my problem statement, basically the implementation of global module index. Coming to my first coding phase, I worked on understanding why modules, global module index is required and how its performance, how it can be used to improve performance by finding out details about the modules and identifiers. So I found and compared the number of modules which get loaded with and without the global module index implementation with modules turned on in 3 cases. One is root startup, the second is the simple test, and the third is the geom test. Again, for the 3 cases, I found the identifiers which cause these PCMs to be loaded, as well as the methods which call load PCM loading these modules. And I also found a set of root identifiers which are not in STL and libc, which require the loading of these modules. I looked into various failing tests during the global module index implementation. Initially, there were about 450 tests which were failing, and on cleaning the code, this reduced to about 50. I also compared the time and memory footprints of the module implementation with and without global module index. And one thing that I found was without RDIC PCMs, a lot lesser modules get loaded at root startup time. I then, during the second coding phase, worked on finding the RDIC PCMs which get loaded for the 3 cases, root startup, simple, and geom test. RDICs are basically generated by rootling, and they are used to efficiently store information needed for serialization. And this was done to find out why global module index shows better performance without these RDIC PCMs. During this phase, I also developed a script which could tell us the modules and libraries loaded by each test or tutorial run by CTest. When this script is run, a folder called loaded libs is created in the build directory, and this contains a set of files where each file is named after the test or tutorial name and contains the modules loaded by that corresponding test. I again worked on fixing failing tests during this phase, and with change which can be seen in that given link with modules turned on, a few of the failing tests were fixed. Another temporary solution we found for fixing most of the failing tests was adding a few modules to the Fix Me modules list. These are a set of modules which should not be loaded but at startup time, but loading them fixes a lot of tests, and hence it's a temporary solution. Coming to the performance measurements during this period, as you can see for the CPU time, both user and system CPU time, the global module index implementation performs better than the current module implementation, and especially without the RDIC PCMs. At startup, there's almost a 28%, at root startup, there's a 28% decrease in time in the case of user CPU time, and in the case of system CPU time, 80% decrease. In the case of simple test, there is a slight increase in system CPU time, and this is because the global module index is loading few redundant modules, and we are working on fixing this. Coming to the memory performance measurements, both resident memory and virtual memory seem to perform better with the global module index implementation as compared to the current module implementation, especially without the RDIC PCMs. At root startup, the 31% less resident memory is used and 44% less virtual memory is used. Coming to my third coding phase, I again worked on fixing a number of failing tests by adding a few more modules to the Fix Me modules. There is also a bug in Clang which occurs in the header search.cpp file when both the pre-built module path and model. I am currently working on understanding why this happens and coming up with a reproducer test for the same in Clang. As can be seen in this graph, summer, the number of failing tests with the global module index implementation has been reduced to a sufficiently decent state, and developed another script to help with the performance measurements. On running this script, again, another folder is created where all the tests or tutorials run by ctest create a file, and the memory and time measurements to run each of these tests or tutorials can be found in each of the files. And the measurements have been extracted, and the latest performance results can be seen in the two links that I have provided here. And graphically, you can,
Peter,
yeah.
Can you give us moments to update, because on my side I am on the previous slide already. You're talking about some other future slides that I haven't seen yet.
Okay.
Does somebody see the new slide, or it's
No,
only
still not. No, still not.
Yeah.
Okay.
Can you just go back and forth? Maybe you can validate whatever is sharing.
Mm-hmm. Do you which slide do you see?
Fixing failing test.
Okay.
Maybe unshare share again.
Yeah, I think I'll share again. Do you hear me?
Yes.
Yes.
Okay. Sorry about that. Okay. Was this the slide you were at? Can you all see my screen?
Yeah, we can see. You need to change the next slide here.
Yeah. Okay. So, yeah, in this particular graph, you can see how the number of failing tests has significantly reduced over the summer. I also developed a script during this time to extract the time and memory measurements for each test or tutorial run by ctest. And the latest performance results can be found in the links provided on this slide. The CPU time performance measurements can be seen in this slide graphically. The system CPU time is actually making a lot of calls, is slightly increasing because of the calls made to the virtual method, which is supposed to resolve a missing symbol. But apart from this, the performance of global module index and the modules is way better than the current state of modules in root. And although root master uses PCH, which is highly optimized, the current global module index implementation can be improved to reach that state, especially because modules are more scalable than PCH. And as can be seen in this slide, root master with modules off, that is root master with PCH as well as with PCMs and global module index have almost the same memory usage, and this is a good indication. And this memory usage can be further decreased because currently a superset of the required modules is getting loaded, so we can reduce the number of modules getting loaded further. To conclude, as can be seen by the graph, the global module index implementation shows promising results to improve performance. However, the current implementation is still not fine-tuned and a lot more modules are being loaded unnecessarily. One way to fix this is by making the identifier module mapping such that the definition is stored first. So in this case, the number of modules loaded can be further reduced, improving performance. This is because there are multiple modules which may contain the definition and declaration of the identifier, causing more modules to be loaded. So this is one of the ways in which the implementation can be further improved. And I would like to acknowledge my mentors for all the help, and it has been a great learning experience for me. Thank you for listening.
Thank you. Sorry for my technical problems. Are there questions for anyone?
Yeah, this is awesome, and I very much like the updated plots. Very nice. I have one question on the plots on slide number, I guess that might be 15, CPU time performance evaluation. Those plots with the black background. So they look very nice. I'm totally not concerned by the CPU time, CPU system time, because it's 1/5 of the user time. I think that's sensible. I don't understand the y-axis, though. I hope this is not seconds, or if it is seconds, it's seconds of something that I don't know what it is.
Okay.
It's likely milliseconds.
Milliseconds. It's milliseconds.
Milliseconds.
Sorry for the
Whoa,
confusion.
hooray. Okay. So that means, and it's doing what exactly? Do you know? Do you remember?
You mean?
What are we measuring? I mean, what does root do? Start up and quit immediately, or does it run HGCal, or does it run CMS Rico?
Oh, this runs all the tests and tutorials which are run by CTest.
Oh, so then it's not milliseconds.
Oh, it is in seconds then.
So this is a complete run. This is a complete run of CTest and the CPU time that running CTest takes.
Yep.
Huh. Okay. I don't know, but that makes it difficult to relate these numbers to something that I know.
And here we exclude the failing tests, right?
Yeah.
Okay, so basically it's arbitrary units for all that I know, because I don't know the, well, we have the numbers in there. Okay, well, that's very nice. That shows that the whole system actually works. Cool.
So
thank you.
So actually the startup time measurements are somewhere before on the slides before this one.
Yeah. These are the startup time measurements, which are labeled root.
Yeah, and those I saw and liked already. I don't know what happened between this week and last week, but I totally prefer this week. It's very nice. Okay, so I got to run to the next meeting, but I just wanted to thank Arpitha for this super cool work. I really hope that we'll have it soon in root proper, but that's not for Arpitha anymore, I guess. Let's figure that one out. But it's really fantastic to see that the Klein guys are going into the right direction, and that you managed to make this usable for root. Thanks a lot, and ciao. Talk to you soon.
Thank you soon.
Bye.
Thanks. Anyone else have questions?
So, Arpitha, you're going to keep the Excel spreadsheets alive for a while, right? Because we may start optimizing this tomorrow, but we may start them optimizing towards module performance in 6 months. So I count on you to keep these documents alive for a while.
Yeah, they will be.
Okay. Another thing that I wanted to point out is, since you are doing work in the area of LLVM, one thing that might be interesting is to take a look at the LLVM developers meeting. They have some student grants, and if you want to go and learn more about the LLVM, Clang, modules, whatever, you just apply if the deadline is not passed. Or even if it's passed, you just send an email to Tanya Lattner and she'll tell you what to do.
Okay.
Maybe that's interesting for you to follow up on.
Yeah, I'll do that. Thank you.
Sure. And if there are no other questions or comments, I just want to thank Arpitha once more. I was impressed by the amount of progress she did. To get the concept, and all the useful work will be actually integrated quite soon, and the scripts and the correlations of the data that you produce are going to serve us quite well for the next, I don't know, 6 months or so to fine tune the global module index. So thanks again.
Thank you.
Yeah, thanks again. Okay, so we have one more. I don't know how to say your name. Is it Raghav? Am I anywhere close?
Hi, it's Raghav.
Great.
Can you hear me?
Yeah, no problem.
Great.
Let's see. Can you share? You want to try sharing your slides? Otherwise, I can try again, which ended badly last time. But
Let me try. Can
that
you see this?
Yeah, no problem.
And now?
Yeah, I see your slides.
Great.
Yes.
Okay.
Okay, so I think we didn't. So you've been working with Maurizio Perini, who we didn't attract. But anyway, you're a Open Lab, CERN Open Lab student, so a bit different from the others who, and you're also have been sort of associated with IRIS-HEP via an IRIS-HEP. So not your time at CERN has been connected with IRIS-HEP, at least financially. So that's why you're here in this meeting, and you've been working on neural networks for the CMS high granularity calorimeter. So I'll let you take it from there.
All right. Thank you for the introduction. I'd like to apologize first of all for joining late. I didn't realize it was a video call. But anyway, so my name is Raghav Kansal. I'm an undergraduate at UC San Diego, double majoring in physics and computer engineering. And this summer, I've been working with Kinga and Maurizio on using deep learning to simulate the hits in the HGCal detector. And more specifically, my project has been to develop a new graph generative model to simulate these hits. So just briefly, as I think most of you might know, the HGCal stands for CMS Phase 2 upgrade. This is what it looks like. You have the 3 components at the top and a prototype module. And it'll be replacing the Hadron calorimeters in CMS, but in the NCAP. So it's a pretty astounding piece of technology. I just like to mention two aspects which are relevant to my project. So first of all, as you can see in the calorimeters, the data which they collect is quite sparse. And so this is important because most of the current work being done at CERN on generative models for detector data is using convolutional neural networks, which treat this detector array as an image essentially, because a convolutional neural network or CNNs are meant to work with images. Or more abstractly, you can just think of them as a three-dimensional matrix. So this detector array is represented, or each pixel in the detector array is represented as an entry in the three-dimensional matrix. But since the hits are so sparse, most of this matrix is just empty. So you end up wasting a lot of time and space manipulating and storing useless information when you're using a CNN. And this is a problem quite general to most detectors at CERN. Something more significant and specific to the HGCal is its irregular geometry, which means it's quite difficult to represent this detector array in a 3D matrix in the first place. So essentially the point is that CNNs are inefficient for this task, and this is because you're trying to adapt or conform this data to an existing architecture meant for images, whereas ideally,
Sorry, I didn't see slides changing, so.
Oh, you can't see any of them changing?
I was about to interject the same.
Okay.
You could just tell us when you're going to the next slide, maybe. I guess you're on slide 11, probably. Maybe 10.
I'm on 6.
Oh, I'm way ahead of you then.
Maybe I can.
It just,
share my
for me, it just
screen.
started updating, actually. I thought. Are you in?
It doesn't change.
Yeah, just try sharing again. Maybe it'll work better. Okay.
I think I'm sharing my full screen now.
Yep. Good.
Yep. I think I see the title slide.
Do you see it in full screen now?
Yes.
Okay, great. So I'll just
There we
skip
go.
ahead to slide 6. Okay, can you see everything?
Yes. Thanks.
It's transitioned. Okay, great. Okay, so I think I was here. So the whole point of this, the whole point here is that the CNNs are inefficient because we're trying to conform this data to an existing architecture. But most successes in deep learning have come from actually adapting the architecture to the data. For example, convolutions for images and recurrence for sequential data. So with that in mind, we are proposing graph neural networks, which instead of a vector or a matrix, take as their input a graph. And the idea is to represent the hits in the detector data as nodes in a graph. And since we're working, this will allow us to work with just the hits, which means we have a very sparse data representation. And it's generalizable to any detector geometry. And overall, it's just a more natural representation of the data. The issue is that there haven't been any generative models published yet, at least. So my project was to develop one. And just for your reference, the HGCal data looks like this. We take the 100 hits, the highest energies, and their angular coordinates and energy are the features which each node in the graph represents. And since developing a new model, especially a generative one, is hard enough by itself, to simplify my task initially, we first mapped this problem to the MNIST, or handwritten digits data set, which is just handwritten digits, 28 by 28 pixel black and white images, or grayscale images, sorry, which is the standard introductory data set usually used in machine learning to test new models. So I essentially sparsified this by taking the 100 pixels with the highest intensities and analogously taking the XY coordinates and intensity as the feature vector for the nodes. And the generative framework I used are called Generate Adversarial Networks, or GANs, where two networks are being trained simultaneously. You first have a generator, which takes random noise as its input and tries to produce a realistic looking sample. And it's helped in this process by a discriminator, which tries to distinguish between the real samples from the data set and the samples that the generator has produced. So as both these networks are trained over time, we essentially have a feedback system where both networks are trying to improve each other until eventually we should have a generator which is able to produce realistic looking data. And in practice, this has worked really well on a variety of data sets. For example, the MNIST one, as you can see, that we have pretty realistic looking handwritten digits. Something more impressive perhaps are these faces, which are quite indistinguishable from real faces, but these are all just are completely fake, produced by a GAN. And as I said, there has been work done on generative models at CERN using GANs, which, for example, these are some slides I took from Federico and Sophia's presentation and on their work using GANs to simulate data for the HGCal, I believe. So these are some thoughts comparing the GAN data and the real data. For example, on the left you have the energy distribution along the z-axis of the HGCal, and as you can see there, the generated data matches the distribution of the real data quite well. But as I said, these are using CNNs and a detector with a much simpler geometry. So for the reasons I mentioned earlier, we believe graph neural networks will be much more efficient for the HGCal. So I've been working on different architectures for the generator and the discriminator in this GAN, specifically for graphs. So I'll just run you through some of the architectures I tried. First, I just used the regular neural networks just as a baseline, which the generator of this GAN just takes a noise vector as its input and produces the 3 features for each of the 100 pixels as a vector, and the discriminator takes that and tries to evaluate how realistic that is. And here you can see some sample outputs of the generator as it's being trained over time, and they're all just noise. So clearly this didn't work. I also tried a CNN just to see how it'll go, which again produces the 3 features for each of the 100 pixels, but as a matrix this time. And it actually works pretty well as a classifier, where a classifier is where the CNN is trying to identify which digit it is. So at over 90% accuracy as a classifier, but as a generator, again, it was just all random noise. So I kept the discriminator, I kept the discriminator as a CNN because of how well it worked as a classifier. The discriminator is essentially just a classifier, but classifying whether it's real or fake. But I tried some graph generators. For example, one I tried was where the generator starts off with just a noise input vector and iteratively keeps adding nodes to an empty graph one at a time until it has 100 nodes with the 3 XY intensity features. And it adds them using an RNN, if you know what that is. And the output here, again, these aren't digits, but hopefully you can agree that it's learning some kind of structure. It's better than just a random noise, which we were seeing before. I also tried a message passing generator, which starts off with a randomly initialized graph of 100 nodes, where their features are initialized randomly. And basically, the generator has each node in the graph take the information from its neighbors and aggregate that to update its own feature vector. And it does this a few times until eventually it outputs the 3 features we want for each node. This is called message passing. And the output here, finally, you can see that the generator is able to learn how to produce digits. However, it takes a very long time for it to be able to get to this point. And also what's worse is that as you continue to train it, it's very inconsistent with its outputs, and eventually it will collapse into whatever this is. So my hypothesis here was that clearly the generator has the capacity to produce these digits, but it's not learning very well how to do this. So I thought maybe the discriminator or the CNN as a discriminator is not very insightful for the generator. It's not able to learn what it's doing wrong. So I replaced it with a message passing network as well, which again takes the graph as an input, aggregates information between the nodes, and outputs how likely it is for each node to be part of a real or fake graph, and then combines all that for the final value. And so this finally was actually able to work pretty well. The generator was able to produce threes quite quickly and consistently. And what's also nice is that the digits are quite diverse in their shape, which is something you'd like from a generator. And in summary, I developed a GAN for graphs, which was surprisingly successful on this Studio HGCal dataset. And all that's left now is to apply it to the HGCal data, which is what I'm working on right now. So I'd like to thank my supervisors and the IRIS-HEP Foundation for funding me. And if you have any questions. Yeah.
Well, that was very interesting. Thanks. Anyone have questions? I have one, if not. I'll go ahead and ask mine. I guess it went by too fast, what you meant by message passing.
Oh, sorry.
Can you just, maybe you just have to say what you said again, and I'll understand what you meant.
So message passing generally is just any form of graph network where the nodes communicate with each other. And my specific network has firstly, the generator iterates over the graph a few times. And in each iteration, each node takes all its neighbors' features and its own, and uses all that to come up with a new feature vector for itself. And it does this for a few iterations until finally it outputs just the X, Y, and intensity features for itself.
Oh, I got it. Okay. And what it's using is decision metric. What is its decision metric in doing that? It's I guess it works the same way as the other approaches, but
so it aggregates the information using this function, which is just a regular neural network, which is the parameters of which are trained.
Okay.
And then it updates the updated feature vector using a recurrent neural network based on the aggregation.
Okay, thanks. That's really interesting. I guess I hadn't seen that before. Anyone else with questions or comments? I don't hear any. Okay, thanks again, Raghav, and thanks to all three speakers. I think these were all really nice projects that we heard about for the summer. So hopefully they can continue in one form or another after your summer work. So thanks again, everyone.
Thank you.
Bye.
Bye.